Hello and welcome to Section 4, Part 2. In the last part, we covered techniques for two of the objectives of high-velocity IT. And today we are going to cover the techniques for the remaining three objectives. So we begin with techniques for resilient operations. Digital products should be available for use whenever needed. Failure is inevitable, but preparation is necessary. Emphasis is on faster restoration of service as compared to time between failures. Overall resilience is determined by resilience of individual components. Lack of resilience may cause loss of revenue, reduction of pricing, additional support costs, and damage to reputation. Resilient systems are an expectation due to consumerization of IT and availability of the cloud. The message here are digital products and services should be available whenever they need to be available, and there will be failures. And in HVIT, restoration needs to be fast. There will be failures and there will be maybe frequent or less frequent failures, but it is more important to restore them as soon as possible so that the value leakage is minimal. Of course, we also need to avoid frequent failures. And many a times, availability and resilience, these depend a lot on individual components. So it may be very difficult to say that a certain data center is 99% available. So there needs to be clarity on what that 99% really means, because there are so many components within a data center. Lack of resilience, again, as we can expect, it can damage reputation, increase the cost, etc. And therefore it becomes an expectation, because additionally, due to nowadays cloud technology and other technology which is commoditized, there is an expectation that these technologies and environments will be constantly running with minimum flaws and minimum outages. Resilience is connected to availability, performance, and security. Availability is a percentage, and the mean time between failures and the mean time to restore. The availability percentage is difficult to measure and usually unreliable. Let's take an example. Let's say we are telling a customer that downtime was 2%. Typically, formulas are used. But normally, these things do not give any meaning to the customer unless we can connect to their impact. So, for example, it may mean that a certain service for them was not accessible and certain transactions could not be performed. And availability could also mean things like what is the frequency for each downtime duration. For example, downtime of half an hour, how many times it happened? Downtime of 2 hours, how many times it happened? And there could be other metrics like productivity downtime. How much was the productivity loss for the users? Rather than an outage of a system or an outage of a service. So it's important to consider these aspects rather than using the typical traditional metrics. Performance, time to load a web page. These are examples of performance. To execute a data query from a database or to complete a batch process. Batch process usually have fluctuating loads. Can the system really handle those different fluctuating loads? System is available, but the load may cause some slowdown. Therefore, the technology may have to scale up automatically. Traditionally, it was not automatically scaling up, but now it is possible with the cloud technology. Security, number of breaches, like hacks or violations to port data on the port, unexpected data on the port. The maturity of control monitoring, procedures to detect vulnerability and prevent vulnerability, those things, and ability to analyze logs to identify risks and breaches. Usually security operations people, they are continuously analyzing the logs to detect security issues which already happened or are likely to occur. And based on that, they can think about preventing them through problem management and also increase the controls, etc. Now let us understand some of the techniques for ensuring resilient operations. These are technical debt, chaos engineering, definition of done, version control, AI ops, chat ops, and SRE, site reliability engineering. Let's go through them one by one. You might have noticed that in this course, High Velocity IT, there are a lot of technical concepts coming from the software area rather than just from the operations area, typically in IT service management. Technical debt is one such terminology. What it means is the total backlog accumulated by choosing workarounds instead of system solutions that would take longer. As an example, let's say a team is developing a quick fix because of urgency, and the fix could be for speeding up a slow application. There are two ways to speed up a slow application uh, with a given solution. Either we can do a quick fix or a properly derived fix. A quick fix is more likely to be weak in terms of its performance, and eventually the system may degrade after some time, as and when more and more such fixes are applied to the system. Therefore, such accumulation causes technical debt. So for example, a quick fix may lead to data corruption, which again needs to be fixed. And again, a quick fix for data corruption may lead to something else. So the debt increases. Ideally, solutions should be developed properly in due time rather than hurrying it up. But sometimes it may not be really possible because of certain expectations of internal management or external stakeholders. The backlog that is required to fix damage incurred when repairing or enhancing software. A proper fix for a workaround may never be developed. Sometimes we have to live with such a fix. So it's important to decide whether to remove the technical debt or not. Let's say about 30 different fixes have been put in, quick fixes, and these have led to technical debt. So at some point in time, a decision should be made whether all these 30 quick fixes which have caused technical debt should be addressed in one go, meaning there should be refactoring of code wherein the entire code should be looked at and completely fixed once and for all for at least those 20 to 30 quick fixes which we went in. Another approach is to take the technical debt small portions at a time. Look at some of the code, remove the debt. Look at another portion of the code, remove the debt, and do it in stages or phases gradually. But that may take time. This debt can also occur during software development when deadlines lead to shortcuts. It is therefore the cost involved to improve the software plus the cost of incidents also. Debt is acceptable to some extent until it accumulates to an unacceptable level. Software entropy. Entropy means the degradation of software. If you see below here, decline in software quality when changes are made to it. So software entropy is very relevant to HVIT because the term HV, high velocity, itself leads to technical debt, can lead rather. As compared to a non-high velocity environment, there is more likelihood of technical debt and entropy in HVIT environments. And there is large software investment in HVIT to bring up modern technologies and develop high performing software, etc. And these demands also change as per the market. In the exam, you have to know these concepts to a reasonable extent in order to answer questions wherein you have to understand the situation in the question and conclude whether it's a technical debt or related to version control or related to minimum viable product and so on. And sometimes in some cases you may have to give a solution that could be a situation, and you have to propose whether we should do a minimum viable product in this case or try to remove a technical debt, etc. So therefore understanding these concepts becomes important for the exam. Reducing this technical debt leads to fewer incidents and resilient operations. It also contributes to valuable investments and fast development. Less debt means investment is worth it. The investment is not lost due to value leakages. Preventing the debt also increases the speed of development, because when there are defects coming in, it slows down the pace of development. There is more attention on the defects, and maybe the attention is diluted on newer features. Therefore, this debt should be recognized, qualified, and quantified, meaning we can qualify it as either complex or simple, or high priority, etc. It's short and long-term risks assessed and decisions made as part of software product management, including a budget to repay the debt. Because corrections require a budget. We will look at the concept of budget afterwards. There is something known as an error budget. We will also see from now on, for some of the techniques, the practices which are applicable. So for technical debt, which are the practices applicable? And in the exam, you could have a situation or a question wherein you have to identify which practice should be applied, or which practice is related to the technical debt in this situation. Therefore, and because we have so much information here, you might require some self-study to look at each and every entry here to understand which practice can be applied for working on technical debt in a given situation. There may be a few questions like that in the exam, because remember, practices are connected to these techniques. So we'll take a look at some of them. These practices are applicable here, and it may be also difficult to memorize each one of them. Therefore, reflecting on how certain practices may be helpful would be a better approach to tackle this. So for example, knowledge management. How is it connected to technical debt? Ensuring all relevant stakeholders have access to up-to-date information about technical debt. So as long as you understand the general purpose of each practice, you should be able to figure out in the exam which practice should be selected as the correct answer. Risk management. Because we understand what risk management is, or we will understand afterwards, recognizing the impact of technical debt on new or existing risks. Also, risk mitigations may create technical debt. A solution to remove a risk may also create technical debt. Service desk. User communication needs knowledge of technical debt and plans to improve it. The user may have to be told that this is a workaround, and we will have a solution afterwards, a resolution afterwards. Project management, running projects. To remove the debt, there may be some projects. And again, projects can result in new debt. Information security. Debt can influence the way controls are made, because debt could lead to incidents. Therefore, additional controls may be necessary for some time. And those controls can also cause issues if they are too complicated controls. Like for example, blocking too many ports can lead to other issues. And business analysis, because that is about gathering requirements and proposing solutions. Therefore, the solutioning aspect would have to look at reducing the technical debt. A solution may be required quickly, but should we incur technical debt just for the sake of speed? There are some more practices coming in. Portfolio management, because this is about investment. Therefore, it's about whether we should invest in removing the technical debt. Infrastructure and platform, because this is a lot of technology related. It's about focusing on technical aspects like component changes. Software development, this is a core of it, to use to do refactoring of code to remove the debt. Problem management, while there is debt, how can we identify solutions to fix incidents due to the debt or prevent incident due to the debt? Improvement, which is natural of course, and incident management to fix incidents arising due to debt. So we will see this coming up in many more techniques going forward, the applicability of practices. Next topic is chaos engineering. This is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. It's like creating a bit of chaos intentionally in environments, maybe in a development environment or a test environment or a live environment. Of course, when we do it in live environment, some communication may be required beforehand, but the disturbance will not be too much. There's no point in creating extreme chaos. So how do we do this? 4 steps. Define the steady state. What is normal behavior? Assume that this will continue, this normal behavior, but introduce variables that reflect real world events. For example, in real world, there could be slowdown. So create a slowdown. And then try to disprove this assumption that steady state will remain always in perfect condition. And then once we introduce variables to disturb it, then we can find out how to fix it so that it doesn't happen afterwards. But again, this introduction of variables should be done carefully. We can't just stop the application, for example. But if that is necessary, then some communication may be required. And the stopping is not intentionally stopping it. The stopping is due to other factors, due to some other incident type of situation. What are the principles? Build and hypothesize around steady state behavior outputs. So very similar to the 4 steps there. These are connected to those steps. Vary the real world events. Take different events which are possible. Run experiments in production. Automate experiments to run continuously. Yeah, let them keep on running, and eventually the system could become more stable as a result of analysis of those incidents and fixes for those incidents. Minimize the blast radius. This is important. Not to create too much damage. As an example, for chaos engineering, let's say we will increase the load on the system. Let's say it's a retail system for ordering products, and we expect hundreds of people to place orders. We will increase the number of orders using chaos engineering tools and increase the load and see what happens. Is the system able to take that load? Again, we can do it based on service level agreements also. If the service level agreement is up to a certain load, then we don't have to really go beyond that load. And also another example could be reducing the network bandwidth and check what happens to the system. But then remember the limited radius for impact. So do it cautiously. So it prepares the team for random failures. These are some of the benefits. It encourages redundancy, makes systems stronger, and therefore increases confidence to move towards more complex systems. Very interesting, this one makes people more confident. It uncovers weaknesses before they turn into problems by introducing realistic conditions in a controlled manner. Addresses most significant weaknesses proactively before they impact customers in production. Now, what about these disturbances which are intentionally created? Will they impact customers in production? As much as possible, it should be minimized. Users may feel a slight change in the behavior, but their business should not stop. As long as it is within the SLA range, it should be okay. Maybe these things should be done sometimes at a given time window. And maybe in peak hours also it should be done. So some principles and policies should be applied. As you can see, there is a lot of information on this topic. One of the open source cloud testing tools of Netflix for chaos engineering is Simian Army, the best known tool set for chaos engineering. Of course, there are many more tools which have come up. There are other tools. There's another one which I remember is Chaos Toolkit. And this Simian Army is a set of tools, is a tool set. Therefore, within this, we have something known as Chaos Monkey. One of the tools in this is Chaos Monkey, which tests the resilience of IT systems by intentionally disabling components in production to test how remaining systems respond to the outage. So as monkey, which are naughty, they keep jumping and keep doing funny things. That's what this does. And for example, it could be stopping some of the virtual machine instances for the application and see what happens. While it may disrupt operations, it contributes to a resilience in the longer term. Imagine if this disruption happens in real time, then all of a sudden people have to scramble and come together to resolve that incident. But in this case, people are already prepared that we are going to disturb and we are here ready to take immediate action. Yeah? And they may already be prepared with some solutions. What can go wrong? And therefore, these are the solutions for it. Because in incident also, people are prepared anytime. But here, they're prepared with different solutions which have been experimented. There are other monkeys like conformity monkey. This is like a compliance type. Latency, this is like a time duration disturbances. Doctor, this is like health checks. Security. Janitor, this is like cleaning up. It's like removing up some virtual machines, yeah? Or cleaning up memory and see what happens. But the main thing is a chaos monkey. Janitor monkey, it doesn't disturb the system. These other ones are basically helping to keep system in optimal condition. Once again, there are several practices here. There are quite a number of practices which are applicable for chaos engineering. This could be an important one. Monitoring and event management is a key practice for chaos engineering. Chaos should be created only with preparation. Therefore, there may be additional monitoring necessary when chaos tools are used, because this monitoring should flag up outages which are being caused because of chaos engineering tools. Imagine there is no monitoring, it's even worse then. Risk management, incident management, problem management, measurement and reporting. There could be some kind of measurements in terms of what can be experimented when creating chaos. Service level, this is also important. The degradation of the service should be done properly so that it doesn't exceed the acceptable levels of degradation. Therefore, some discussions may be required as part of the contract on how to use these tools. Because otherwise, customers should not be surprised that, oh, we didn't know that you're using these tools and we are actually frustrated with those interruptions, small interruptions now and then. There will be risks due to chaos. They need to be reduced. There will be incidents during chaos, and they will require fixes. But more proactive problem management will happen with better preparation. It can lead to better validation of requirements and testing of components, better design, architecture improvement. By the way, architecture management is not just technical.